Okay, in this second video, we're going to look at how to solve for forced response. Okay, so in the previous video, we used modal analysis to do natural frequencies and mode shapes. Okay, so now we just need to add another function or another analysis, which is the harmonic response. Okay, so the harmonic response gives you the steady state response of the force in a given frequency or a given frequency range. Okay, so if you click that, so you automatically create another module and share the geometry and material and all the settings that we had for the model analysis. If you go back to your workspace, you see there's another module being created and automatically shared those settings. So now, unfortunately, the boundary conditions is not shared, so we have to redefine the boundary conditions, which is fairly easy. Just select those points and say fix. So now it's fixed. Okay, so let's have a look at what's required. So the requirement is to apply a torque about y direction at this node. So we're just going to do that. So the point is here, at this point here. So I just need to apply a moment. Okay. So where do you want to apply? So at this point, yes. Then to define a moment, there's a few different ways. So the way we want is to by the components, because we're given the moment about y direction, and the moment that was given is 250 Newton meters. So now the direction is also shown in here. So that's the external force we're going to apply, and then we want to set up what is the frequency of that forcing. Okay, so you can set one frequency or a range of frequencies. So in this particular example, we were asked to do from 0 to 8 Hertz with 200 increments. Okay, so we can put it here. We put minimum is 0, maximum is 8, and the interval is 200. Okay, so that's it. So that's the setup, but we also need to define what we want to see from these results. Okay, so initially we want to see the total deflection of the deflection shape of this structure under each of the frequency. But secondly, we want to have a bit harmonic response analysis or a spectrum. So we want to get some frequency domain. Okay, so we just add frequency response, and for example, we want to see deformation. Okay, so just say deformation, and for example, if we look at the deformation at this point, so just say geometry, I want to look at this point, and what is the orientation? So we basically want to, for example, look at the z direction, so off the plane, and we probably also look at x as well. So deformation, same point, and in x direction. Okay, so we look at two things. One is in out of plane z direction, and the other one is in x direction. Okay, so that's all set. So I just need to solve it. Just run the simulation. It will take a little bit longer time than before, but it should be fairly quick. You see it's done. So now we look at the total deformation that we saw before. So these are the forced deflection shape. It's been greatly exaggerated because if you look at the numbers, it's actually very small, and we are using a scale factor of 1200 by default. So you can have the alto, which is slightly smaller, but if you have 1, the true scale, you probably won't see anything, even you play the animation. So that's the true scale. Don't be scared with that exaggerated deformation. But that's the deformation that you will see under the force of this. This one is very small. Okay, let's have there are 200 of frequency that's been simulated, but how do we know which one is critical? Okay, so that's by looking at the frequency response. So under the frequency response, this is in Z direction. You can clearly see there are 3 peaks corresponding to 3 natural frequencies. Especially those natural frequencies also correlated to the phase change of 180 degrees, which means they are natural frequency shapes. I have to note this plot is slightly different to what we're getting the sine wave sweep in the experiments, because that sweeping test is so this is always steady state, but the experimental sweep test, the system might take a bit longer time to get into the steady state, and therefore the peak is not as sharp, and also the phase change is affected by the damping ratio that exists in the system, which we haven't modeled yet. So this is the ideal case. And we look at X direction. There are some modes that we didn't see, which is this one, because this is the in-plane mode, so it only deforms in X direction, so it doesn't show in the Z direction figure. Okay, so now we can pretty much say these are the natural frequencies, sorry, these points are natural frequencies, including this one. So we can then go back and look at the deformation shape. To get the frequency that we have those peaks, we can just go back into this list. So you got the amplitude and frequency put in together, and especially we can look at the change phase, the phase angle changes. So you can see this 0.96 Hertz is probably is this peak here. It's our first resonance case. So we just go back to the natural frequencies, the total deformation shapes, and we just look for that 0.96 Hertz. And then we just retrieve that data. So this will be the actual forced deflection shape. Note it is very close to our second out-of-plane mode that we see from the model analysis, because obviously that involves a lot of torsional deflection, which is our external force. Okay, so that's the harmonic response. If you're only interested in one frequency, so you can always, under these settings, instead of having a big range, you can put a small equal minimum and maximum, and just put the intervals as 1. Then it will just give you the response in that frequency that you want. So, but obviously scanning a range is also an option. Alright, so that's for the harmonic response, which gives you the steady state forced vibration response. Thank you. So next video we're going to look at a transient response.